应该是能，我这边
我还没经历。OK，
哎，是不是有这个？你得把你
OK， 我明了。
哦，不是，把你的专业把
我把什么关掉？
这样啊。你其实你离我的话筒很近，你就那个什么吧，你就把你的 disconnect 你的声音就行，你全都关了。
你想用你这个话筒说对吧？
对。
OK，
你把你的声音全关了。
OK， 我都关了。
行，
那还能听到吗？
我这边显示应该是可以的。
OK。那如果有别人提问，我这能听见吗？
他应该能通过我这儿开始。
OK。
今天我们这个11:50之前结束。
OK， 对，因为我看你也有报告。
对。Okay, let's start. It's a great pleasure to have Zhi-Hao Zhang from USTC to tell us about classification of SPT or SCT orders. Please.
Okay, first I'd like to thank Professor Wang for inviting me to give this talk. In this talk, I will talk about the classification of SPT and SCT orders based on the boundary bulk relation. In the last week, we have talked about the classification of 2D spatial dimension, symmetry protected topological orders, and symmetrically enriched topological orders with a finite onsite symmetry G. And we using the idea of gauging the symmetry to classify these SPT and SCT orders. And now we are going to briefly review the basic ideas. Okay. Roughly speaking, SPT or SCT order is a topological order with symmetries. The symmetries represented by the category of symmetry charts, and they form the category rep G or rep GZ. When the symmetry is photonic, this category is rep G, and when the
这不没声音。等一下，没声音。我要不是因为左上角没解除静音。他自己是没有解除静音，但是他应该连的是我的话筒，应该能从我这儿传出声音来。
所以
那个有人说正常，有人说没声音，那有人正常的，那应该是没什么问题。那我这个没关系，你继续讲吧。
Okay. So this is a category of symmetry charts. And then for this SPT order or SCT order, we can consider the particle-like topological defects. They can be fused and braided together, so they form a unitary braided fusion category. And this topological defects contains the symmetry charts, so C contains E. And for SPT orders, by definition, C must be equal to E. And by the anomaly-free condition, we will only consider anomaly-free SPT orders and SCT orders. So the Milgauss center of C is equivalent to E. Then we try to gauge the symmetry. After the gauging process, we obtain a topological order whose particle-like topological defects form a unitary modular tensor category. Okay, because for the topological order, the anomaly-free condition means it's the topological defects form a modular tensor category. And also M contains C. So we say M is a modular extension of C. And moreover, M satisfy a minimal condition in the sense that the Milgauss centralizer of C in M is equivalent to E. And also we see the minimal modular extensions of E form a finite abelian group. And the unit is given by the Dirichlet center of E. It is a trivial modular extension. And for a general modular, for a general braided fusion category C, the minimal modular extensions form a set that is either empty or a torsor over the group of minimal modular extensions of E. And for the example, when E is rep G, the minimal modular extension form a group which is isomorphic to the group cohomology H upper 3. And when E is the S flag, the category of supervector spaces, the minimal modular extensions form a cyclic group of order 16.
So may I have a question? So for the fermionic symmetry, the rank GZ, the Z is space function in the 2D.
Z is the fermion parity.
Fermion parity.
Yes, it's a constant number of fermion. Yes.
I have a question.
Okay.
Your fourth point and the condition about either empty or closer. So my question is, what is the requirement of C? It's just Z2 of C equal to E?
Yes.
Okay.
So in the second remark, why you consider particle-like defect in the 2D, the symmetry should be the line defect.
This 2D spatial dimension.
Oh, 2D spatial.
Yes. Okay, so these are what we have known in the last week. But also the idea of gauging the symmetry works very well. There are still some questions. So the first problem is an SPT or SCT order is a well-defined notion before we gauge the symmetry. The gauging process just produces another topological order that is not this SPT or SCT order. So this gauging process is not a direct description of the theory. So there should be a macroscopic description of SCT or SCT order without gauging the symmetry. Okay. The second point is if a SCT order cannot be gauged, and physically we see it has a 't Hooft anomaly, and then this idea does not work. We cannot gauge. And in this case, the pre-diffusion category of particle-like topological defects has no minimum Mordic tensions. And mathematically, we have known some examples. Okay, physically we know an SCT order can be gauged if and only if its bulk is a trivial SPT. And it means the 't Hooft anomaly is the same as the bulk. So this gives us another idea to describe SPT or SCT orders. And this is the theme of this our talk.
Sorry, I missed your talk last week. So we're engaging symmetry here, we're engaging the symmetry in the 2+1. Engaging in the 1+1.
Gauging in 2+1.
In 2+1.
Yes. Yeah, but you can gauge in any dimension, yes. Okay, so this new idea is based on an important principle it's called the unique bulk principle. It says each ND topological order has a unique bulk, and this bulk is an n+1D topological order. Okay, it seems this principle is very trivial, but it does tells us many things. The first is if the mathematical description of bulk and the boundary topological orders are known, then there should be a mathematical description of how to obtain the bulk from a boundary, right? And this is called the boundary bulk relation. And if we know the precise boundary bulk relation, then the description and the classification of a boundary series of a given bulk is also known. This is directly from the boundary bulk relation. Okay, so the idea of the classification of SPT or SCT orders in all dimensions is clear. So first we need to know the precise mathematical formulation of the boundary bulk relation. And then we view an ND SPT order or ND SCT order as a boundary of the trivial n+1 SPT order. If there's no 't Hooft anomaly, okay, so we can gauge it. But now we try to view them as boundaries of the trivial n+1 SPT order. Then by the boundary bulk relation, there should be an explicit description and classification of ND SPT orders. Okay, this is the main idea. So we try to start from the simplest case, n equals to 1. In this case, the boundary bulk relation for 2D topological orders and their 1D boundaries is well known. This boundary bulk relation is first proved by Kitaev and Kongliang in 2011, and then proved by Kongliang by using annual condensation. It gives mode independent proof. Okay, this boundary box relation says, suppose we have a 2D topological order, and its particle-like topological defects form a unitary modular tensor category denoted by C, and it has a 1D boundary topological order, particle-like topological defects form a unitary fusion category A, then C is equivalent to the junction center of A. Okay, this is a boundary box relation. It says the bulk is the center of the boundary. Then we can study the classification of 1D SPT orders based on this boundary box relation. The first, as before, the symmetry is still represented by the symmetry charges, which form a symmetric fusion category E. Then we consider the particle-like topological defects. It forms a unitary fusion category A, and A should contain the symmetry charges in E. Moreover, the symmetry charges are transparent in this 1D phase, so the symmetry charges indeed live in the junction center of A. So we have inclusion from E to the junction center of A. And we know the trivial 2D SPT order is described by the trivial minimum modular extension, which is given by the junction center of E. By the boundary box relation, the junction center of A should be the same as the junction center of E. Okay, so there is a Brady equivalence from the junction center of E to the junction center of A, and the following diagram commutes. The following diagram means this Brady equivalence preserves the symmetry charges.
Okay. So you use the results of classification of 2D SPT order, right?
Yes.
And this result is obtained from gauging.
Yes. Yeah, the 2D SPT order is described by the minimum modular extension, the trio one, the junction center. Okay, and now we have this equivalence from the junction center of A to junction center of E. Then, therefore, BIMSA dimension should be the same. This tells us the inclusion from E to A is equivalence. What does it mean? It means there is no non-trivial topological defect. So the 1D anomaly-free SPT orders are all 1D SPT orders. Here, SPT simply means that A is equal to E. This is a well-known physical result and proved previously by other physical methods. So we only need to consider 1D SPT orders, and that's taking the category A to be the category E of symmetry charges. Then the 1D SPT orders with symmetry E is determined by the Brady equivalence phi on this junction center of E, and the following diagram must commute. And all these Brady equivalences form a group denoted by this automorphism group. It is the automorphism of the junction center of E that preserves the embedding from E to the junction center. And this group just classifies the 1D SPT orders. Recall that 1D SPT orders form a group, and it should be the same as this group. And we also know this group is isomorphic to the Picard group of E. And these Picard groups are also well known for mathematicians. For bosonic symmetries, E is equal to rep G. Then this Picard group is isomorphic to the group cohomology H of 2. This result also recovers the usual cohomological classification of bosonic 1D SPT orders. And for fermionic symmetries, E is rep GZ. It is also computed in the following result. And this also agrees with the physical classification result. So our classification recovers the usual physical classification using matrix product states. And our approach is only a categorical approach. And here is a remark about the Hofft anomaly. Recall the Hofft anomaly of SPT order means the bulk is a non-trivial SPT order. So If we have a 1D SPT order, but it has Tohoft anomaly, it is to be described by a unitary fusion category A, equivalent with a central embedding from E to A, just as before. And now its bulk is a non-trivial minimal module extension represented by M. And there is a Breuil equivalence phi from M to trivial center of A, and the following diagram must commute. The left-hand side is M. It is a minimal module extension just described in a bulk 2D SPT order. But we can still count the Frobenius-Perron dimension, and we see M, the Frobenius-Perron dimension of M has the square of the Frobenius-Perron dimension of E. And so still the Frobenius-Perron dimension of A is equal to E. Sorry, this diagram has some problem. The right-hand side, there should be the trivial center of A. Okay, so, but still we have the Frobenius-Perron dimension of A is equal to that of E. So A is equivalent to E, and M must be equivalent to the trivial center of E. So M is indeed the trivial minimum module extension. This tells us there is indeed no Tohoft anomaly. In other words, a non-trivial 2D SPT order has no gap symmetry preserving boundary. If it has, that should be a 1D SPT order, so there should be a contradiction. So the boundary of a non-trivial 2D SPT order must be gapless or symmetry breaking. This is also a well-known physical result and proved by other physical methods. Now it follows from our observation of boundary bulk relation.
I'm sorry, a naive question maybe. So why is phi an equivalence?
This equivalence means the bulk of A. A is our 1D theory. Its bulk is the trivial center of A, and M is the bulk. M is a 2D SPT order. So equivalence just means they are the same.
Okay, so implicitly you can maybe I want to make sure of this fact. So you can view any SET or SPT as a topological order, right?
After gauging the symmetry.
But A is simultaneously your SET and the topological order when you forget this symmetry, so that you can compute the center of A, right?
Yes.
So I will make sure. So A is a 1D SET.
Yes.
And after you're gauging the symmetry of 1D SET order, you get another topological order.
Right.
So described by B, right?
Right.
And then, what is M? Z1 of A or Z1 of B?
Z1 of A.
Of A?
Yes, Z1 of A.
So you are using the boundary population.
Yeah.
And you can, so this process does not relate to gauging.
Yeah. Only the bulk is gauged. The boundary is not gauged.
M is gauged.
Yeah, M is a gauging gauge theory, and A is not gauged.
Okay. Oh, okay.
Yeah, there's some mystery. I have to say there is some problem in this approach, but you may find the right approach in the end of my talk. Okay, so now we are going about to talk about the classification of SPT or SET orders in higher dimensions. So the first step is still the boundary bulk relation. But in higher dimensions, we need to include more topological defects other than the particle-like topological defects to describe the topological order. Okay, so, for example, if we consider a 3D topological order, the particle-like topological defects can be fused in 3 different directions, so they form a E3 algebra that is a symmetric fusion category, and it must be rep G or rep GZ by a theorem of Deligne. But for a given finite group G, there may be many different 3D topological orders whose particle-like topological defects form that G. At least we know the Diagraph-Witten series traced by a focal homology class. They satisfy this condition. So the particle-like topological defects cannot characterize the 3D topological order. So how to use defect to characterize topological orders? The solution is to include more, they may be string-like or membrane-like topological defect. So first we'll consider a 2D case. We know the particle-like topological defects in 2D topological order from unitary modular tensor category, denoted by M. Now we try to include 1D domain or 0D domain between them. So we obtain a very large mathematical structure. It is called the unitary fusion 2 category. And now we denote it by sigma M. So what is this fusion 2 category? Its objects are 1D domain walls. So in the following picture, the P, Q, S, T are just 1D domain walls, and they are also string-like. Okay, they are spatial dimensions in 1. And the 1 morphisms are 0D domain walls between these 1D domain walls. For example, A is a morphism from P to Q, and B is a morphism from Q to S. And T, there is a morphism C. C is from T to the trivial domain. Here, trivial domain does not appear. And X, here is a particle X. But, oh, sorry. Oh. Okay, this particle X can be viewed as the domain between 2 trivial domain walls. Okay, so all particle-like topological defects can be viewed as 0D domain walls between 2 trivial 1D domain walls. So they also appear in this fusion 2 category. Okay, and these string-like topological defects can be fused horizontally. For example, you can fuse T and P. And then the associated 0D domains are also fused together. From if you fuse T and P, then C and A are also fused. So this is a monoidal structure of this fusion 2 category. But as you can see, the 1D domains cannot be braided, so it is not a braided fusion 2 category. It is only a fusion 2 category. And we also know that 1D domain walls in M can be obtained by any conversation, so they are called condensation descendant. But this means all 1D domains are completely determined by M. So indeed, you have not included more information, just the same. So these two characterizations are equivalent. The first one is to describe a 2D SPT order by particle-like topological defects. They form a unitary modular tensor category. But you can also characterize it by the 1D domains and 0D domains. They form a unitary fusion 2 category. Okay, this unitary fusion 2 category, sigma M, is also called the condensation composition of M. And for mathematicians, sigma M is just the Karoubi completion of the one-point looping of M. And it is also equivalent to the 2 category of finite semi-simple right modules of M. Okay, so this is sigma M. And similarly, in M plus 1D topological orders, you can also consider codimension 1 and higher topological defects. They can be fused and braided, so they form a unitary braided fusion N category, or unitary modular N category, by the anomaly free condition. But if you consider the codimension 1 and higher topological defects, so you must include the string-like topological defects, though they can only be fused but cannot be braided. So they form a unitary fusion N plus 1 category, sigma C. This is also called the condensation completion of C. And as in 2D, using C or sigma C to characterize the N plus 1 topological order are equivalent. Now we can state the boundary box relation in higher dimensions. So in this case, we have an N plus 1D box topological order. And In this n+1D bulk, we consider the codimension 2 and higher topological defects. They form a unitary modular tensor n category. And it has an ND boundary A. This ND boundary, we consider the topological defects of codimension 1 and higher. So we just consider all topological defects on the boundary. So they form a unitary fusion n category. Sorry, there's a miss n category. Okay, and the boundary bulk relation says C is identified with the junction center of A. Yeah, it's very similar to the 2D case, but all topological defects form higher categories, not one category.
So I have a question.
Yes.
So the string sample for the n category is also well defined?
It is well defined up to the notion of n categories. Maybe you have to see the notion of n categories not well defined.
So now I just want to see, how to compute. For example, the fusion 2 category, how to compute.
Yes, there are some examples. For example, there is a paper of Kong Liang, Tian Ying, and Zhou Shan. They just compute the junction center of two vectors twisted by a 4-cycle omega. It describes the 4D digraph-Witten theory. Yes. Okay, so we can come back to the classification of 2D SPT or SCT orders using the boundary bulk relation. So if we have a 2D SCT order with a symmetry given by a symmetric fusion category E, the symmetric fusion category is just the category of symmetry charges. But now we need to use a boundary bulk relation, so we try to include more 1D domain walls. They are the condensation descendant of the symmetry charges. And now we have a symmetric fusion 2 category, sigma. And we still consider the particle-like topological defects. They form a Briley fusion category C, and C contains E. And still we try to use a boundary bulk relation, so we need to include 1D domain walls. And now we have a fusion 2 category sigma C. And also sigma C must contain sigma E. And for SPT orders, C is equal to E, and sigma C is equal to sigma E. And as in the 1D case, the symmetry charges are transparent, so the inclusion just factors through the junction center of sigma C. And mathematically, E is contained in the Milgren center of C. So after you do the condensation completion, it factors through the junction center. Okay, then the bulk of this 2D SPT order is the trivial 3D SPT order, but now we just gauge it. So it should be described by the trivial minimal modular extension of sigma E, which is given by the junction center and equipped with this canonical embedding from sigma E to its junction center. Then, by the boundary correlation, we must identify the box 3D topological order with the gauge theory of the trivial 3D SPT order. So mathematically, this is a Briley equivalence from the junction center of E to the junction center of C. And this identification should preserve the symmetry charge. So we have the following cumulative diagram. And this Briley equivalence phi, just as in the 1D case, it should characterize the SCT order. And in particular, for SPT orders, we have C must be equal to E, so this phi is a Briley autoequivalence, just as before they form a group denoted by this automorphism group. It is automorphism of the junction center of sigma E and preserve the canonical embedding. And we see this group must classify the 2D SPT orders with symmetry. So now we have two classifications of that 2D SPT orders with symmetry E. The first approach is by gauging the symmetry, and the classification is given by the group of minimal modular extensions of E. And the second approach is based on the boundary bulk relation. The classification is given by the group of braided autoequivalences of the junction center of sigma E, and they preserve the canonical embedding. So there's a natural question that are these two approaches equivalent? Okay, so mathematically, this means these two groups should be isomorphic. The group of minimal multiple extensions and this automorphism group. And this is a mathematical conjecture and deserve a mathematical proof. Okay, so we try to write down this conjecture. We have a symmetrical function category E, and now we have a group of minimal modular extensions, and it should be isomorphic to another group which contains braided autoequivalences of the trivial center of sigma E, and they preserve the canonical embedding. And moreover, if we consider SPT orders rather than SPT order, then we have a braided function category C whose Milgrom center is E. And we consider a set of minimal modular extensions of C, and we see this set should be isomorphic to another set, that is the braided equivalence from the dream field center of the dream field center of sigma E to dream field center of sigma C, and they preserve the embedding from the sigma E. Okay, and it is also possible that the minimal modular extension of C does not exist, and in this case, it says the braided equivalence from sigma E, the braided equivalence from the dream field center of sigma E to dream field center of sigma C also does not exist. And as far as I know, this conjecture has been partially proved by Theo Jotunfred and David Rutter. Now I will not give a proof, but I try to clarify the relation between these two approaches. And so physically, if I have a braided equivalence from the dream field center of sigma E to dream field center of sigma C, this braided equivalence can be viewed as a 2D invertible domain wall. I denote by Wi-Fi. Okay, the dashed line in the following picture. And this Wi-Fi is canonically associated to this braided equivalence. If C is equal to E, Wi-Fi is an invertible domain wall between two trivial 3D SPT orders, and so it is a 2D SPT order. This 2D SPT order is just the one corresponds to phi. And in general, for general C, this equivalence phi is a tossor over the automorphism group. Yeah, because you can stack another automorphism and get a new one. And how do we get the gauge theory? The gauging process can be recovered by close this phi. We just fuse the two boundaries, sigma E and sigma C, along these two boxes and this invertible domain wall, so we get a 2D theory. It should be the gauge theory, sigma M phi. This M phi means the gauge theory associated to this equivalence phi. So mathematically, it says this relative tensor product of fusion two categories are equivalent. So this gives a map from this braided equivalence, the set of braided equivalence to the set of minimal modular extensions. And the equivalence of these two approaches says this map should be an isomorphism. Okay, and this idea of boundary block relation also leads us to a unified classification theory for SPT and SPT orders in all dimensions, and possibly with higher symmetries and possibly with the Houghton anomalies. Okay, for n is greater than 1, any SPT order or SPT order with higher symmetry. We suppose the higher symmetry given by a symmetrical function n category R, so it is not given by a finite group. And possibly it has a Houghton anomaly, but without gravitational anomaly, so it characterized by the following data. So first we need a unitary function n category A. This is a topological defect, the category of topological defects in all codimensions. And also we need the minimum modular extensions of R. It determines the Hofft anomaly. It is the bulk n+1D SPT order.
Excuse me, I have a question. So, for example, for the minimal modular extension, do you know how to do it for the 3+1 topological order?
It is still an open question. Yeah. But we will conjecture the minimum modular extensions of 2 RAP-G are given by the force cohomology of this group. And this is still an open question. And finally, we need a Brady equivalence that says the bulk of A is the same as this SPT order. Okay, so, and we have this commutative diagram, which means the symmetry charges are preserved. Okay, if we allow M to be non-minimal, we also obtain the description of SET orders, which is so-called gravitational anomaly. The gravitational anomaly means the bulk may have non-trivial topological order, so the bulk is a SET order, so maybe not a minimum modular extension. This physical theorem immediately provides many precise mathematical conjectures on higher fusion categories and minimum modular extensions. So, for example, it suggests us to study the higher group for minimum modular extensions of a symmetrical fusion higher category. And if this symmetrical fusion higher category is n-RAP-G, so what is n-RAP-G? So 1 RAP-G is simply RAP-G, and 2 RAP-G is sigma of RAP-G, and so on. Okay, so we just expect that the minimum modular extensions of this higher category are the n-RAP-G, so this should be an n+3 group. And this K homotopy group should be the group cohomology H upper n+2 minus K. Okay, and you have many of these higher groups, and maybe there should be a structure like spectrum or something.
I'm sorry. So when n equals to 1, the minimal extension form a 4 group according to your.
Yes. It's not very clear because you try to consider minimum modular extensions and functors and natural transformation. You maybe only get a 3 group. Yeah, and this is because the functors between the minimum modular extensions are they can be realized by the modules of this RAP-G. So they just form the Picard group of RAP-G. And the Picard group can be lifted by a Picard 3 group. So you get a 4 group. Okay, so we have a very good approach of classification of SPT of SET orders, but there's still some problem. The problem is if an ND-SPT order has no anomaly, it is well defined without the bulk. If you try using a lattice model to realize this SPT order, you cannot see the bulk in the lattice model. This is very mysterious. So you see the SPT order has a bulk, which is a trivial SPT order. But now, if you realize it by a concrete lattice model, the bulk cannot be seen. So the question is, why does this approach work? And where does the bulk? The answer is the bulk is virtual and just lives in the time axis. You can imagine that you try to rotate this bulk to the time axis. This sounds crazy, but it has a name called topological weak rotation. And this virtual bulk is also called the categorical symmetry. So it just describes the symmetry of this theory. And this topological weak rotation gives us a holographic duality between n+1D topological orders with ND boundaries. and ND-gapped quantum liquids. Here, quantum liquids include topological orders, SPT orders, SET orders, and spontaneous symmetry breaking orders. And even the gapless quantum liquids can be included in this process. For 1D SPT or SCT or spontaneous symmetry breaking orders, this virtual bulk also contains observables in the long wavelength limit. So microscopically, they are called topological sectors or operators. Then just in the 1D phase, we find all observables they form an enriched diffusion category. The objects are particle-like topological defects or just topological sectors of state. And for two objects, we can consider their Hopf spaces. The Hopf spaces are topological sectors of operators. The operator just map one sector of states to another sector. And these topological sector of operators live in another category B, so this is the B enriched category. For example, in the 1D Ising chain, this is the simplest phase with Z2 symmetry. There are two gapped phases. For the symmetric phase, the ground state is non-degenerate, and you can find the observables from the enriched category, which is graph Z2 enriched in its trivial center. And for the symmetry breaking phase, the ground state is twofold degenerate symmetry. The observables form an enriched category, which is VAX Z2 enriched in the trivial center. Okay, but I will not give the details here. Okay. And mathematically, the topological recruitation provides a one-to-one correspondence between the pair, here B and S, or B is a Brady fusion category and S is a fusion category coupled with a Brady functor. And the enriched fusion category obtained by this pair BS. This correspondence can be promoted to an equivalence between two symmetrical monoidal two categories. Okay, given by my work joined with Kongliang, Yongwei, and Zhi-Hao. And for 1D SPT or symmetry breaking orders with an onsite symmetry given by a symmetrical fusion category E, the categorical symmetry B should be given by the trivial center of E. And this overlay means just reverse the breeding, but this is due to some technical reason. Yeah, so the categorical symmetry is simply the trivial center of E. And then S should be a boundary of this B, so it is a fusion category, and the trivial center is equivalent to this trivial center. So it is induced by a Lagrangian algebra in the trivial center of E. When E is rapid, we know the Lagrangian algebras in this trivial center are classified by these pairs H omega, where H is a subgroup of G and omega is a two cohomology class. Okay, this exactly meets with the classification of 1D SPT and symmetry breaking orders classified by physicists using other physical results. Moreover, we can define the center of enriched categories and the center of enriched monoidal categories and the center of enriched Brady monoidal categories. The centers are defined using the universal property in the two categories of all enriched categories. And in particular, we can compute the trivial center. So for every fusion category E, we consider the enriched category of E enriched in its trivial center. And this enriched fusion category, its trivial center is VAC. So this gives us the correct boundary population. This says the bulk of a 1D SPT order is trivial. So we get the trivial topological order, the trivial 2D SPT order. Trivial 2D topological order. So this is the correct boundary population. So the bulk of this SPT order is indeed trivial. So in higher dimensions, we also expect the topological okay.
Just a question. So the bulk of, if I consider the 1D ICT, so values in normally non-trivial in that sum.
So in 1D, there's no SPT order if no anomaly.
For example, the 2D SPT.
Okay.
Then the bulk can be non-trivial.
If there is anomaly, then the bulk is not trivial. So the bulk is the same as anomaly. So.
No, I mean even just the virtual. You did this weak representation. The virtual bulk can be non-trivial.
Yes, the virtual bulk is always non-trivial. The virtual bulk B is a categorical symmetry, so it describes the symmetry of this phase. So if you have a symmetry given by a group G, this B is the trivial center of rep G. Or in 2D, it should be the trivial center of 2 rep G. Okay. Yeah, but this bulk is rotates to the time axis, so you still take the trivial center of this enriched category. This center is trivial.
Yeah, that's a bulk enhancement. Good.
Okay. So in higher dimensions, you also expect the topological recruiting spelling. This idea leads us to study enriched higher categories, which is not a well-defined notion. There is some definition of enriched higher categories, but maybe not the one we need. So this is an ongoing project joint with Liang. Okay, so that's my talk. Thanks for listening.
Okay, thanks for the great talk. Are there any questions? So let me look at, is there any question online? You can unmute yourself and ask. So let me.
Can I have a question? Sorry.
Yes.
Can you hear me?
Yes.
Oh, yeah, I want to ask, if your so your 1D SPT or SCT order, the symmetry is given by a symmetric fusion category. So I want to ask if this symmetric fusion category is like vec G omega, so then the virtual bulk is somehow anomalous, right?
I
mean,
sorry,
and
you mean
mathematically
the symmetric fusion category E is vec G omega?
Yeah. If in this case.
Maybe vec G omega is not symmetric, but you can, yeah, but it maybe has a generalized fusion category symmetry given by vec G omega. Yeah. Well, yeah, go on.
Yeah. I'm asking just mathematically the trivial center of the vec G omega enriched in trivial center of vec G omega is vec, right?
Yes.
So
yes, the following result is this center, this result holds for every fusion category.
Yeah. So
for E is vec G omega, it is also true.
Yeah. Then such enriched category will describe a anomaly-free 1D system with like some fusion category symmetry.
Yes.
Okay, I see. All right. Thank you.
More question?
I have a question. So when you say some SPT or ST is the bulk of another SPT or SCT,
yes,
do you assume the symmetry are the same between among
yes.
the bulk?
Yes.
But in reality, are there some cases that the symmetry are not the same?
I'm not sure. I don't know such examples, but maybe the symmetry has spontaneous symmetry breaking. But if the symmetry is explicitly break, maybe it is also possible, but
when you say symmetry breaking, does it mean that the symmetry are not the same? Since some symmetry may be the
if the symmetry is spontaneously break, the symmetry is the same. But if the symmetry is explicitly break, they are not the same.
And one group is the subgroup of another.
Not necessarily, I think.
Oh.
Maybe when say symmetry, we mean the symmetry of the Hamiltonian or the symmetry of the ground state. So they may be not the same. If not the same, we see there's a spontaneous symmetry break.
As long as it is spontaneous symmetry breaking, it should be in the same block. Still be captured by this trivial center of G.
Yeah. This trivial center.
Because G is spontaneous, broken on boundary.
Yeah. Yes.
Any more questions? But if not, let's thank the speaker again. Okay, that is the